gave the last time.
All right, so
This is not oh yeah, this is not the one. Last time.
yeah, we are already on YouTube.
This is not
Okay, today we have Dr. Hybrix Bindele, and we are waiting for his PowerPoint. The talk is already live on YouTube for those who are not here and who want to listen to us. Got it?
yeah,
There we go. That's the right file.
yeah.
And I believe we should just start. Some people are not here yet, but they will just have to catch up. We have 5 minutes gone already.
All right. Well, good morning, and thank you for being here. I've decided to talk about this particular topic. It is a collaboration work that uh, I conducted with a colleague at Georgia State University, Yichuan Zhao. It is about rank-based estimating equation with non-ignorable missing response via empirical likelihood. The idea relies on considering a regression model. Okay, we have a regression model, and we are mainly interested on the estimation of the model parameters. Okay, whenever we have some missing responses, and when it comes to missing data, okay, we have to be able to predefine the missing mechanism. Okay, among others, there are three most important one. Okay, we have the so-called missing at random, missing completely at random, and missing not at random. And the talk today will focus with the latter one, missing not at random. Missing at random, in fact, means uh, the missingness of an outcome um, can only happen with respect to some fully observed covariate. Okay, whenever we have a regression model, you have a response and covariates. So if the missingness of a response is dictated by some covariate, we say that we have missing at random. On the other, missing completely at random, a missingness of an outcome is completely independent of the data itself. While on the other hand, missing not at random, a missingness of an outcome, I would say, could be happening by the information of the outcome itself. So mathematically, what that means, if we get to define an indicator observation that I called here delta to be 1 if the outcome is observed, and 0 if the outcome is missing. Okay, so we can define some the probability of observing the outcome has pi of xi, which is the probability of delta equal to 1, given the data in some sense, okay, y and x. So we comes to the situation of having missing at random if y and delta are independent condition on x. On the other hand, missing node at random, there is no possibility of trying to separate delta and y, no matter what. So they're gonna still be dependent no matter what. Only missing completely at random, the probability of delta equal 1 does not depend on x on y. They are completely independent. Okay, so there are some other type of missing mechanisms that exist out there, but these are the 3 ones that we really look at in the missing data literature. So the main point here is to try to estimate how a BIRA 0 in the model here, or BIRA in the model, in the presence of some missing y's. Of course, we get to remember that whenever we have missing data, okay, before some work were conducted in this particular topic, okay, one way was to handle the missing situation was just to consider the complete case analysis. What that means, we delete all those observations having some missing responses, and then conduct the analysis as if the entire data was observed. But we do know the consequences of doing that. Okay, we lose power. Okay, power of statistical analysis. We are likely to end up with biased estimate when we do that. So whenever people started considering this topic, they say, what could we do to try to get some reliable estimate whenever we have a large number of missing data? Okay, well, whenever, of course, we have a small number of missing data, right? It is proven that the complete case analysis, okay, still work. But if it is a large number of missing data, the complete case analysis is not something to be advised to follow. So something needs to be done. So comes the notion of imputation, which is in fact trying to come up with some plausible values to fill those missing ones. So for instance, in the very simple case of mean imputation, if we have a univariate data, okay, we can consider the mean, and then we fill those missing ones by the mean. But there is a problem with that. Whenever you do that, you have to make sure that you consider a randomization procedure. Because if you do not randomize, those missing values that you have replaced by the mean are fixed. So at some point, it's gonna give you some kind of variance that will not be the correct one, because you might end up with a smaller variance, think that you are doing something good, but in fact you are not, because those values do not have any variance. The variance corresponding to those values gonna be equal to 0. So in practice, how do we do that? We use the distribution of the missing, the distribution of the complete case estimator. It means whenever you have the model, whether you are using the least square, you estimate BIRA through the complete case analysis. And then once you impute, you use the distribution of the estimator, which is in fact normal, and use it to randomize those particular value that you've obtained through the imputation process. Okay, that will make the variance of the model acceptable. Well, that was just a small remark. Well, as I said, our main point is try to come out with a robust estimate. Come out with a robust estimate. And we do know that whenever we have a regression model, this is just a simple regression model. Why I'm calling it simple? Because it is not like the one that I considered last time. The one that I considered last time was a single index model. This one is just a general regression model where we have some function G, okay, which is known. And our interest is the estimation of BIRA. And we are interested on a robust estimation of BIRA. So 3 techniques were considered. We have the LS, we have the LAD, and we have the rank-based method. Well, we know that the LS, while it is simple, if we have heavy tail distribution there, or in the presence of unusual observation, what I mean outliers, and sometimes leverage points, we end up with biased and inefficient estimate. In order to correct that, one could use the LAD. The LAD is known to be very robust. Unfortunately, it is inefficient when it comes to deriving the estimate of the variance of the estimator. It is not very efficient. That is the problem. So come the idea of considering a rank-based approach. So the rank was introduced through some extension of the Mann-Whitney procedure. I think you guys know that when it comes to comparing 2 populations, okay, when we talk about the Mann-Whitney test. That same idea was extended to linear model and behind. So for this model, for instance, one, we consider the residuals. Okay, so we could define a rank-based objective function, okay, which is given here. And this objective function was proven by Jekyll in the 1972 to be continuous, to be convex, but the convexity comes with some assumption on the function, the regression function itself. The regression function has to be convex because whenever Jekyll considered his case, he did assume that he has a linear model, and we do know that a linear model is convex. So that makes the function itself to be convex. So why am I saying that? It is possible that we'd be interested on the uniqueness of the estimator. If we are interested on the uniqueness of the estimator, okay, we can put some condition on the regression function to make it convex, and that will make this objective function to be convex. So this function results in robust estimation. Okay, so definitely in the response spaces, okay, the how do we call it? The influence function that resulted through this function is bounded, which means that this objective function result on robust estimate, whether we have unusual observation in the response spaces. Something could happen whenever we have an outlier in the covariate space. If there are outliers in the covariate space, the influence function is not bounded. So you can make it, you can add a weight, which gonna make the influence function to be bounded. Okay, and in fact, in terms of the residual, okay, this is a pseudonorm. Okay, and you can see this expression that I have here as a norm of small a here. It is expressed like this. Okay, it is not entirely a norm because the first condition of being a norm is not satisfied. But the last two conditions that we check for a norm are satisfied. That's why we say that it's a pseudonorm. And I have an example here. This is some data, and the data contains some outliers. So I decided to consider two fit. Okay, the LS fit and the rank-based fit, and you're gonna see the difference. Why am I saying that? If you look at this data, there are some outliers there. We can see outliers. Okay, the red line here is the LS fit. You can see that it is being affected by the few outliers on the top there. It is being pulled. While the rank-based, which is the blue one, is not. Okay, the rank-based is the blue fit. It is not being affected by those few outliers that we have there. And we can see the curve on the bottom here, okay, and shows just what I mentioned, the fact that the function in the linear case is convex. Okay, this is the graph of D and theta, which is telling us that the function is convex. Well, let's go back to doing something about the missingness. As I said at the beginning, we have some missing y's. Okay, the idea is to impute and then use the rank-based to estimate the unknown regression parameter. So we've defined what is the observed probability. That's what I call pi of x, y here, which is the probability of delta equal to 1 given x and y. This probability, in the case of the missing node at random assumption that I mentioned, I say that there is no way you can separate y and delta. Even when you control x, delta and 1 gonna still be dependent in the case of missing node at random assumption. So you can see that you need to consider such missing mechanism into your data modeling to be able to come out with something meaningful. But the functional form of such missingness might not be known. But remember, okay, we decided to define delta to be equal to 1 to make it an indicator to be equal to 1 when we have missing y's and 0 when how a y is observed. So we can think of considering some logistic propensity score to take into account the missingness. In some sense, okay, we want to estimate that missing to come out with some probabilistic way to insert the probability of y being missing. So as we define it, so two things can happen. Okay, we can assume that delta can follow a logistic model, which means we can write the functional form of pi xy. Okay, as I wrote it here. But when we do that, we end up with a situation that we get to worry about. We do introduce a parameter here. Remember, we are in the situation where we have missing y's. You get to worry how you're gonna estimate this parameter, gamma. So we do have a problem of model identifiability because of this new parameter that you have introduced. And how are we going to estimate it? Because there is no data on it. Remember that this model that you are using here, the only way you can estimate this gamma if the y's are available, but they are missing. So the idea is to do a follow-up sample, to come out with a follow-up sample of use an independent sample. It means if you are doing a particular study, somewhere else they could do the same type of study and use that particular independent sample to estimate this gamma. That's one way you can do it. Or do a follow-up sample Go back to those people that you survey. Let them help you answer a particular question that you were trying to ask. And the new data that you're gonna get, use that to estimate this gamma. And once this gamma is obtained, okay, we could use it's gonna help us to estimate this pi of xy. It's gonna help us to estimate this pi of xy.
Sorry, is h of x a known function?
Well, h of x is a non-function. Okay, it is just a function of x.
Yeah, we
Okay.
also have to choose somehow, no?
No. Well, it can be linear, it can be quadratic. Well, that's why I call it h of x. Okay, the expression can be linear, it can
I
be
understand. I'm
quadratic.
asking if in the model it's something that we get to decide for.
Not really, because of remember when we have a logistic, what is this h of x? It is a linear function, is that correct? For a logistic model. So I don't want to limit myself to that particular case. So it can be some function of x plus gamma times y. If you look at this relation, you're gonna see that if gamma equal to 0, you go to what assumption? To missing at random. You can see that y will be independent of delta. Is that correct? If this gamma equals, so it is this gamma that is making the missing node at random assumption in this case. Yeah. So the point that I'm making here is the estimation of this gamma rely on those two things that I said. Either you consider an independent sample or a follow-up sample. Okay, that's the cost that you have to pay in terms of conducting the estimation whenever. So when I was thinking about this, I don't know, I think it was in 2019 when I decided to think I think this work was motivated by the work by some guy at I think it should be Iowa University. Okay, a paper by Kim and Yu. Okay, where they did look at this topic on missing node at random, and through a discussion with Professor Zhao, we decided to do something about it. But when I was thinking about it, I said, well, we have the observed distribution. It means that we do have the distribution of delta equal to 1 condition on x and y. What is known here, what is not known is the distribution of delta equals 0, which is the missing part, condition on the data. So how can I do something about it? I thought about the Bayes theorem. Okay, there is a way to express the distribution of the probability of delta equal 0 given x and y, okay, as a function of the probability of delta equal to 1 given x and y. So that helped me come out with a fully known non-parametric way to estimate this pi x and y. Okay, this expression that I have here, you can see a kind of kernel type of estimate here. So so it means that when it comes to the imputation, there are still possibility to use the observed data to help you impute the missing ones. Just like for the mean response example that I took, means you take the mean of the one that are observed, and then you start plugging those. That is the idea here. So I use Bayes on, and Bayes gonna rely on the observed part, and I'm gonna have the expression that gonna help me to estimate this pi.
So your alpha hats is based on the observed y values, right? Or the complete values, complete data. So your button, the J, it's on the complete data to estimate this alpha hat.
Yes.
Okay.
Yeah. Otherwise, how are you going to estimate it if you do not have data? So the idea is to estimate the probability of delta equals 0, because that is the one that is of. In fact, you see this pi of xy, which is the probability of delta equal to 1, given xy. Okay, so whenever you write, you use Bayes, you're gonna have this expression to be a combination of the probability of delta equal to 1 given xy, and the combination of delta equals 0 given x and y. So your problem is that probability of delta equal to 0 given x and y, because that is the missing probability. So you get to take into account that part, and you use the Bayes to have an expression that connect both the probability of delta equal to 1 and the probability of delta equal to 0. One, you have that expression, which gonna be just a function of delta equal to 1, because you could replace the probability of delta equal to 1 as a function of the probability of delta equal to 1. That was the idea. But you have to remember that when you use the probability of delta equal to 1, you are in the situation where you have some y's that are observed. You are no longer in the case of missing y's. That is exactly the idea. So we estimate this. Once we estimate this, then we can conduct how this is the estimator. So we can conduct how imputation. Let me see. It look like there is a slide missing here. Looking for an imputation. Oh, I don't. It look like I did not put it. But what I mean, I don't know if I can write something. I don't know if I can write something. But I hope you guys are following. But
yes, yeah, we follow.
the idea is to impute now. So I did consider two imputation scheme. One, which is known as the simple imputation, which is just a simple random imputation, which means I write a new y that I could call y tilde, which is equal to delta times y plus 1 minus delta times something that you use to impute. And you can see that for delta equal to 0, it has to be that new thing that you're gonna use to impute. And for delta equal to 1, it is the observed y directly. So in some sense, you are trying to replace those missing y's by that things that you have used to impute. Okay, remember what I said when I go back to the mean imputation. It means for delta equal to 1, you have the observed response. And for delta equal to 0, it's gonna be your x bar, which gonna be the mean. That is the idea here. That is the regression imputation. But remember what I said in practice. Okay, once you get those new values of y, you get to randomize them. Otherwise, you're gonna have a problem with the variance. Okay, the other imputation is to incorporate the probability, the observed probability into the imputation procedure. That is the probability weighting, which means you're gonna have y tilde, which gonna be delta divided by pi xy times y plus 1 minus delta divided by pi xy divided times whatever you're gonna use to impute. Well, once you do that, then you define your residuals, and then define the objective function and minimize the objective function to get whatever estimator that you need. It can be done through the least square objective function. It can be done through the LED objective function. But in our case, the objective function that we consider here is the rank-based objective function. The only problem is when you do that, you are interested on a robust estimation, which is one thing, but you have also to worry about possible statistical inference about the true parameter by itself. What I mean by that, the construction of confidence intervals and performing hypothesis testing for those regression parameters. And you know that whenever we need that, we get to worry about the distribution of whatever estimator is obtained. What I mean by that, you get to worry about how to estimate the variance of the estimator. Unfortunately, for the rank-based, you do not end up with a simple expression of the variance. Okay, the expression can be a little bit or is a little bit complex. I don't know if I have it. This is, as you can see here, this Bira hat here is our estimator, and we have the distribution here, and this is the variance of our estimator. So if you want to perform, which depends on Bira 0 itself. So if we want to perform hypothesis testing about this Bira 0, we need to estimate this. And the estimation of this is not straightforward. It is a little bit complex. Okay, how do we do that? We use the so-called sandwich type estimator. A sandwich type estimator relies on trying to, because this W Bira 0 here is a limit of some, I would say some expression. So I use that expression, which is a function of Bira 0, but there, instead of having Bira 0 there, I use a plugin estimator. I use Bira, whatever is the estimator of Bira 0, and I plug there. And that particular expression that I'm going to obtain is what I'm going to use to replace this guy. Okay, that is known as a plugin, a sandwich estimator. Well, it works, but it does not guarantee to end up with an efficient estimator all the time. So that was the motivation of this work. And what we know is that if this is a normal approximation approach, because we want we use the normal distribution of the estimator to define whatever the test statistic or to come out with the confidence interval. So the idea is to find a procedure that will lessen the burden of trying to estimate this covariance. And we know that to do that, you use the so-called empirical likelihood. I don't know if somebody have done some work with that within you there. Okay, the empirical likelihood, okay, makes you avoid trying to estimate this estimator. And we know that the idea is we define an empirical likelihood function and try to obtain the Wilk theorem result. Okay, and remember that Wilk was able to prove that whenever we have a random sample, and based on that particular random sample, if we can come out with a well-defined empirical likelihood and show that that empirical likelihoods have a chi-square distribution, you can use that it is easier to use that to build your statistical inference than trying to estimate the covariance matrix. But of course, we know that if you have a normal distribution, if you have a normal random variable, if you square it, you're going to end up with a chi-square distribution. That is the idea. So we were able to do that. So we have this normal approximation, and how do you come out with the empirical likelihood? You see, this is our objective function here. If you look at this objective function below here, and we look at the argument of the objective function here. Okay, you take the derivative of this objective function, differentiate it, you're gonna end up with an expression from which the argument gonna be this vi of Bira 0 that I put here. And use it as a new random variable and define an empirical likelihood on that. Once you define an empirical likelihood on that, it is given here. Okay, what I'm calling L Bira and gamma. And why am I calling it L Bira and gamma? Remember, okay, through the logistic model for the missing probability or the observed probability that we define, we did introduce a parameter that is gamma. That is in the case of trying to estimate that observed probability, okay, using the logistic model. But for the fully non-parametric, gamma is not there. So whenever we have this, at some point, you're gonna have to estimate it, and we did already talk about it. You can use either the independent sample or the follow-up sample to do so. And then once you define this, because you are trying to estimate this, you are not going to end up with a simple chi-square. You're going to end up with a weighted chi-square distribution. And of course, if you have a weighted chi-square, the only problem is to worry about how to get the degree, because when we have a chi-square distribution, the only parameter is the degree of freedom. We get to know how to come out with the degree of freedom.
So there is a typo error for the VI tilde. It should be 1 minus delta I, right? The delta I equal 1, it is missing. Equal 0, it is observable. So it's 1 minus delta I, right?
Where I am
in the middle, you have the VI tilde, that formula.
Yes.
And you have your delta I. I think it should be 1 minus delta I, right?
No, this is delta I. You see this expression here. It is almost the same.
The delta I equals 0, which means the observable. If it is equal 1, it is
This is the weighted empirical likelihood, which is just defined on the complete case. This is not taking into account the imputation. I think that's what it is.
Yeah, if it is for the complete case, that should be 1 minus delta I, right? It is. Yeah, this.
Yeah, thank you.
0, it is observable. If it all the plug in 0 into it, it can give you 0.
We are finishing in 1 minute.
No.
All right.
For the complete case analysis, we do not worry about the missing part. Is that correct?
Yeah. Yes. But
yeah. So yes, the point, I understand what you are saying. However, we get to take into account the probability of missingness.
Yes.
That's why we are trying to weigh it with that delta I.
Okay. Oh, yeah, understand.
Yeah. Now, what you are pointing out is, I think I have talked about it somewhere here. You see, here I'm imputing. Is that correct? You can see this YI tilde N here. Okay. You can see delta IY. So if you put it to be 0, you're going to have something that you use to replace. You can see that I'm using whatever. Yes. Okay. So, and then here is a new objective function. This one is taking into account the imputation. And with this one, the empirical likelihood is given here, this R and J of beta 0. And of course, we get to show that the distribution of this R and J of beta 0 is chi-square. And this is where is the result. And with this result, we can build confidence region of beta 0 directly. And with those confidence region, we can conduct statistical inference about it. And that was, in fact, the main work of this paper. And let's, I think, I don't know how much time do we still have, not many.
We ran out of time already. So.
Oh, you see. So here.
Yeah, it's the 9 to 9:50. So, but I mean, so
so
you can
let's take about 5 to 10 minutes to complete this simulation result. So we made some simulation, and we did consider 3 types of model error distribution: the contaminated normal, the T, and I think the normal itself. When I talk about the T, I do consider a small degree of freedom. okay, to take into account the heavy tail case. Okay, and for that pi of xy, I think Marshall, you did ask what was that your h of x. You can see in each of these expressions, you can identify what is your h of x. Okay, the first one here, you can see that it is this quadratic function. Okay, and in this case, it is just this small linear function. And but we did also consider the case where we deviate from
your model. Case 3 that hold your model.
Like
yeah.
case 3 here, you can see that I do have 0.1 y squared. I'm deviating here and see whether it's gonna affect the procedure. And we did some result. We computed what is known as coverage probabilities and average length of confidence interval. So on the three methods, when it comes to the coverage probability, okay, the nominal level here is 0.95. So the closer to 0.95 is better coverage. And the smaller average length, the more efficient the procedure produce the estimate. And if there is no time, but if you go through the numbers, you will see that the rank base does better than the LS and the LAD that were considered. Okay, so, and you see, I have the two missing procedure, SI for the simple imputation and IP for the inverse probability, okay? In SI, it is just that expression where I'm just multiplying by delta I. While IP is, okay, multiplying by delta I divided by pi of xy. That's the difference. And this slide here is just to help you estimate that parameter that we talked about. Okay, if you want to estimate gamma, okay, you can use it. You can estimate it via a least square or a rank based. But remember that when I said you need to estimate it using either a follow-up sample or an independent sample. So this is the estimating equation that you can use to estimate gamma. And of course, when some of these require some, okay, this is real. This is the real data, and the observation is the same. Okay, if you look at this real data, you're gonna see that. Okay, I'm reporting the length of confidence interval of whatever parameters that we have. Okay, I'm just looking at a linear model, but I'm reporting the length of the confidence interval of the parameters of these covariates. Those are the ones that we have. We have under the three different approach, we have the complete case, the weighted complete case, and the imputation for the two last year. And if you go through the numbers, okay, there is no more time that if you go through the numbers, you will see that we did gain something. And of course, we could see that, you will see that the numbers that you have on the complete case analysis is missing something. You will see that it is missing something, and whenever you compare them, you will see that the imputation has helped to correct that. Okay, and these are some theoretical assumptions that were needed to derive the asymptotics in the paper. Well, I think I'm gonna stop here. Okay. Once again, thank you for being here, and I just want to say that I hope in the future I will have the opportunity to visit Oxford.
Yeah.
You're
And,
more than welcome. So
Thanks for the wonderful talk. Mhm.
yeah, thank you very much.